Docs is generally a really complicated piece of software, right? And to assume that I can just reverse engineer and make design decisions for Google Docs is extremely stupid, and I'm not even going to try and do that. Instead, the assumption here is that if tomorrow I wanted to build out a dummy project like Google Docs, and have some of the core functionalities that Google Docs has, what are some of the more obvious design choices I would make? Now, obviously Google Docs has an insane number of features, and more than that, generally design decisions are taken within the constraints of the architecture that you end up starting with, right? And the architecture that gets built upon the architecture that you end up using, and most designs are built around that architecture. I'm doing none of that here, and the whole point of this is to just conceptually understand the different things to consider while building out Google Docs, and the different things I would consider while building out Google Docs, and just touching on some of the complexity and features that exist in Google Docs more so. So, firstly, to pretty much lay out on things that I would really be touching upon. Firstly, CRUD on documents. CRUD on documents essentially refers to being able to create, read, update, and delete these Google Docs. When I say CRUD operations here, what I actually mean is performing create, read, delete, update on the metadata associated with the doc. So I'm not actually talking about updating the document content itself. I'm actually talking about updating the content that exists here. So the name of this, let's say I call this Anish over here, right? This is what I'm more so talking about. And being able to create a new doc, being able to update a doc's metadata, and being able to delete a document, and being able to have this document load, essentially. So that's the first part. The second part is the parallel updation of docs. And the next 3 points pretty much tie into each other. So the parallel updation of docs, real-time edits in the browser, and conflict resolution. Parallel update of docs essentially means that if I, let's say, write a sentence here, my name is Anish, I should see that sentence here at the same time. And two users should be able to edit a document at the very same time. Now, obviously, being able to see it real time in the browser, obviously, just like we saw in an example. Conflict resolution. So, theoretically, if two people are updating the same document at the same time, there is the off chance that both of them end up editing the exact same part in the document at the very same time. So, figuring out how conflict resolution works is also a fairly important part of even building out a dummy project like Google Docs, because it's important to make sure that the state of the document for every user who is on the document is consistent. So, for example, if I say I see my name is Anish, the other user should not see my name is Anesesh, right? When this user actually sees Anesesh, we need to make sure that the document state is consistent at all times, and that is one thing to talk about, and that essentially ties up into this whole parallelly updating documents and making sure all of those updates reach accurately to all the users who are currently on the document. Firstly, CRUD. Very simply put, this is probably sort of the more intuitive part, that you essentially have API endpoints that edit the metadata associated with this docs. So we'd probably have a database, SQL or NoSQL. We can figure out what that choice is, but some sort of database that we would actually have APIs hit to be able to create documents, initialize documents, essentially update documents, delete documents, and also to be able to fetch document metadata. So fetching the title, I can't think of the other metadata, for example, fetching who all this document can actually be shared with, essentially things of that nature, right? And that's a pretty important part. And it's also one of the more intuitive parts. And these API endpoints sort of thing, this API design, really, this create, read, update, delete, can be translated into really any other application. This is just nothing unique to Google Docs, obviously, but that's one of the fundamental building blocks. Then we move on to the next part, which is the parallel updation of docs. And before I even talk about how this parallel updation would work, the important part is to understand what the protocol that these API endpoints run on, and why that protocol actually does not work for the parallel updating of docs where several people are updating the same doc at the same time. So essentially, the protocol that ends up getting used for these API endpoints specifically is HTTP, right? Simple classic HTTP running REST, running get, delete, post requests essentially, and updating things within a database. Nothing too unique happening there. However, this does not actually work for parallel edits. And let's try and visualize why. So let's say if I'm on a document and I write an edit, right? All of these edits obviously need to reach the other user's browser. So for example, if there are two people, Varun and Aryan, if Varun types in an edit, it also needs to reach Aryan's browser. And this needs to happen, one, not just in real time, but it also needs to happen across every single small edit I make. So for example, even if I type one letter here, this one letter edit needs to reach the second person's browser. If I type in everything here, these edits aren't going in bulk. These edits are one by one reaching this user's, essentially client, in this case, their doc, and gets displayed here after the whole conflict resolution dance happens. Which means that this is actually a very frequent operation because this is pretty much near real time. Now, the HTTP protocol is meant to be built over a request response model, which means that the client requests something to the server and the server receives a server responds back with a response. Let's understand something here. So what's happening here is that I am, let's say theoretically, I was using HTTP and I actually need to send, let's say, this new edit that I made here to the other person who's also on this document. So theoretically, I send out an HTTP request to the server saying, hey, here is my edit, send it to all the other people who are on this doc. But HTTP is not built for the server to send back data to the client by itself. This client has not requested for any data. This client just needs to receive this edit automatically, which means that the server actually needs to send something to the second client who is actually on this doc. And HTTP, being a request response model, only responds to you when you actually request for something. So until this second document actually requests for the latest edits, they're actually not going to receive anything, which defeats the whole purpose of trying to build out a real-time system, because ideally the edits just get streamed to the second person's document, and that's not happening here. And since HTTP was built on this whole request response model, it doesn't actually work here. And besides that, there's also the fact that HTTP has its own network overhead, because HTTP is creating a new request and sending it to the server. And what's happening here is that every single every single letter I type, now in this case, or every single letter I delete, is being sent as a new HTTP request, which creates a lot of overhead. And that's not going to work. And therefore, we actually need another protocol to be able to solve this exact problem. And that is where comes into the picture WebSockets. So WebSockets is known to be a real-time protocol. It's known to be persistent, and it's known to allow bidirectional communication. What do I mean by bidirectional communication? It is basically the fact that when the server receives an event, let's say if I typed something, if Varun, okay, let's just go with the Varun Aryan example. So if Varun types something on his doc, and the server receives that edit, the server can resend that edit back to Aryan, who is also the second person on the dock. And all of this can happen over a single connection. There is no new request being made, there's no new response to receive back, none of that happening. It's all happening on a single connection that Varun and Aryan have made with the server. So HTTP, as I've talked about earlier, being on the request response model, every single time their browser actually makes an HTTP request to the server. However, with WebSockets, you just make one initial request to connect on a WebSocket connection with the server, and after that, the client can send events to the server and the server can send back events to the client, which means that as long as Varun and Aryan have a WebSocket connection with the server, whenever Varun sends an edit to the server, it can reach Aryan over Aryan's WebSocket connection, and Aryan, whenever he types in an edit, it can reach Varun over Varun's WebSocket connection, because the server now has a persistent WebSocket connection that was created by Varun and Aryan's browsers. And this is one of the really cool things about WebSocket. Now, um, that essentially we've talked about the protocol, right? How this entire thing is happening, how the server is sending it back to the client is something we'll come to in the implementation part. But the whole point of introducing the protocol was to understand that for parallel updations or real-time edits, simple HTTP is not going to work, and we need to move to WebSockets, which is a more real-time protocol. Google Docs specifically uses, I believe, Quick, which is based out of HTTP2, which I think also allows bidirectional communication. I'm sure it allows some version of bidirectional communication. It doesn't exactly use WebSockets. However, it's based out of WebSockets, and most real-time applications end up using some version of WebSockets essentially, including applications like WhatsApp, as far as I know, and WhatsApp Web in the browser's case. And that's the protocol that would essentially define how these real-time edits work. Before I would go to the implementation part of how this specific protocol entails in terms of code, the next thing that I want to talk about, and I'm just trying to touch on things before there is sort of the in-depth of how this protocol actually works and how the persistent connection allows bidirectional communication. The next high-level part I want to talk about is file storage. So far we've talked about being able to create these, like the API endpoints that are built over HTTP, which would support creating of these documents, updating of these documents, essentially things like that. And we've also talked about the real-time updates happening over a WebSocket connection. So we have two different parts covered. Now the third main part is, where does this document get stored? Google Docs is, at the end of the day, just documentations, right? These are docs that need to get stored somewhere. Our one option is storing them in a database, a SQL, NoSQL basic database. But that's not ideal. And the reason it's not ideal is because databases aren't built to store files. They're not built to be able to store magnitudes of files, large files, small files, whatever it is. That's not their purpose, right? And the most common place where things like files and folders are usually stored are object stores. AWS has its own object store called S3. Azure, Microsoft has its own object store called Azure Blob Storage. And these are essentially the object stores where all of these files actually end up getting stored. So therefore, all of these files essentially would actually end up getting stored in these object stores. And usually, whenever you store files, you usually get back a URL to this file. And that in itself is what you can actually end up storing in the database itself. So in the database, you can store, the document title, the document, for example, sharing privileges, who all have access to this document, and all the other metadata that would associate with the document, created timestamps, maybe when the document was last edited, when the document was last created, things like that. Because I think you can usually somewhere in Google Docs see when the document was last edited. I'm not sure, but yeah, so essentially all metadata that goes into the database. However, the actual document itself and its content can actually be stored in an object store. And once the document loads onto the Google Docs website, you can then start editing, and the real-time updates would be powered by WebSockets. And we'll come into how that works, but that's sort of the high-level image that we've formed so far. So essentially the next thing, right? Edits storage. So we've talked about file storage. We've talked about the document being created and the document's metadata being updated. And we've also talked about sort of file storage, about where these documents would actually end up being stored, and the protocol, which is going to be WebSockets. However, there's the next part, which is edit storage. The reason edit storage even comes into the picture is because we know that we're going to store the document within an object store like AWS or Azure. However, how frequently do you push edits? So what that means is that I'm always making these edits, right? I'm adding these new words here. So on every request that goes to the backend, so on every WebSocket over the WebSocket connection on every edit that is going to the backend, does it mean that we also push it to the object store right then and there? Do we push the updated file then and there? Well, probably not. And the reason we don't do that is because object stores, sending a request to the object store is an expensive operation. And considering the number of times you would actually be editing a file constantly, it's unrealistic to assume that for every single edit, you would actually send it to the object store. It doesn't make sense, right? And ideally, we'd like to have a slightly better architecture where we can store these edits, and eventually all of these edits get compacted, and essentially all of these edits turn into a real document and then get stored in the file storage in our object store in this case. So our first point, which is we can't keep pushing to object stores. I've talked about it earlier. It's a heavy process to do, and also we're going to introduce a lot of latency. The reason we'll introduce a lot of latency is because every time there is a new edit and the server receives the edit, we're saying that before sending the edit to Aryan, who is the second user on the dock, we also send a request to the object store to update the file, and then we send back the edit. Well, that's unideal because that's going to take a lot of time, and we're going to increase latency, and this is meant to be as real time as possible. Well, theoretically, you could say that let Aryan first receive the edit and then we push to the object store. Well, that's again an ideal because one, if you're constantly creating edits, the server is going to keep getting new requests to actually push to the object store. And secondly, if there is some sort of timeout or if there's something at the network layer that crashes, which means that the request is not able to reach the object store and we aren't able to update the file, well, suddenly it's all broken, right? And this is extremely unideal, and we don't want a system like that. And the same thing applies to if we, instead of an object store, if we push to a database. So for example, if we pushed synchronously to a database, which means that we constantly, when the server receives edits, it pushes those edits to a database, even that's not going to work. And the reason that's not going to work is because of this latency issue, where one, if we synchronously push to the database before Aryan actually receives the event on his client, that's an ideal because it's going to take time. There is a certain amount of time, and the system is not real time anymore. And if we first send the edit to Aryan and then push to a database, well, what if something within the database crashes? So suddenly there is this tail edit that only exists with Aryan and the other clients, but as soon as they refresh the page, they won't have that edit anymore because it's not stored in the database. So that's not going to work. And ideally, we need a slightly more asynchronous system such that these edits can keep flowing, but I also keep updating my database / my object store with all of the edits so that eventually all of these edits end up in the object store and the object store has the correct file that it needs to have. Obviously, the need for async essentially means that we use something called a message queue. And a message queue essentially allows us for this asynchronous communication to happen. And the technology here is really depends on the system itself. Like for this dummy 5 users application, we can use any message queue really, RabbitMQ, Kafka, or NATS, or any one of these message queues. It doesn't matter, or message broker systems basically. But in this case, I'm not going to name a technology simply because it can be anything really. However, the whole purpose of these message queues is that whenever we send out, let's say, a request for an edit, so there is a diagram that exists here. So for example, whenever the server receives a new edit, right, this would be published to a queue, and publishing to a queue is just an O of one operation, aka it's just one send a message to the queue. And essentially what this is doing is that we're not making a network call anymore to the database itself or to the object store, and we just publish to the queue and we send the edit to Aryan, who is the second client itself. And the consumer of this queue, what the consumer of this queue would actually do is put this edit into a database, and we would keep putting these edits into a database. So all the edits Aryan is making, all the edits Varun is making, whoever is making these edits will end up putting these edits into a database. So essentially, the consumer of this queue would actually push edits to the database, and we would have workers which, let's say on a cron of every 30 minutes, actually end up pushing the edits to the database and eventually end up sending all these edits to the file store. In this case, we've assumed S3, could be Azure Blob Storage, or whatever it is really. And that means that all of our edits would eventually live in S3. So essentially, all of our files would actually live in S3, and the worker is doing the heavy work of taking the edits out from this database, making sure they're compacting the edits into the correct state of the document itself, essentially. And eventually, all of this gets to S3, such that every time the new user requests for a document, they actually receive it. There is a race condition here, which means that what if the worker actually ends up taking this every 30 minutes, obviously. However, between the 30-minute duration, the user actually requests for the doc. And that's a race condition that can be handled through a complicated way, which I'm actually not going to go to right now because we're trying to build out a dummy 5 users project. However, that is a race condition to be considered. And sort of the bad solution here is that when the user actually requests for the document, we actually check within the database if there are any extra edits. We compact those edits and combine it with the file that actually exists in the object store, and eventually serve that file back to the user when they open the document, basically. And that's one naive way to handle it. And I will not go too much further into those race conditions because they can get really complex. But that's the idea behind handling edits and storing edits and making sure everything eventually ends up within our object store, S3, Azure Blob Storage, or whatever else it is. All right, the next part to understand about is understanding how WebSockets actually scale. Now, we talked about, or generally how WebSockets work even. We know that the protocol that we're going to use for real-time edits is actually WebSockets, and it's important to understand how WebSockets actually work before we even understand how WebSockets can scale, and why WebSockets scaling is an interesting problem statement. So how WebSockets essentially work is when you send out the request to the server to initiate a WebSocket connection. So when Kunal, who is the first user, sends out a request to create the first WebSocket connection. So instead of an HTTP connection, a request response model, a WebSocket is basically an HTTP upgrade. So what Kunal tells the server, or Kunal's browser tells the server, hey, I'm trying to create a WebSocket connection which is persistent in nature. And what the server does is that it actually generates a WebSocket object. This object is of a specific type and cannot be stored in a database of sorts, essentially. And what we end up doing is, on the server itself, in memory, we end up storing that for this document ID, this is the user who exists, and this is their WebSocket object. And how this works is that this WebSocket object is actually what is used to send back a response from the server itself, or to essentially send back data from the server itself. So let's visualize this, right? So we have Kunal and Aryan who are on the same document. Kunal initiates a WebSocket connection from, let's say, their UI app, which reaches the server. When it reaches the server generates this WebSocket object, which is this custom type object, which gets stored in, let's say, something as simple as a hash map, right? For the sake of now. Let's say it gets stored in a map. And what happens here is, within this map, we end up storing Kunal along with the WebSocket object that he holds. Aryan then tries to connect to the WebSocket to the server, and what happens is Aryan's WebSocket object, I will remove this away here. Aryan's WebSocket object actually ends up going again within this map. We can ignore what this is here. I'll come to what that is, but we can. So essentially, Aryan's WebSocket object is also created, and they're both stored to server one. Now, what happens is, when I create an edit, when I, let's say, change a letter here, this edit reaches the server, and it will always reach the same server because WebSocket is a persistent connection. And this sort of gets complicated, and like this sticky connections conversation gets complicated. I was recently learning more about it while trying to do something for essentially TCP, where we were trying to create sticky connections within this is going down a tangent. I'm actually going to stop right here. But basically, we're going to assume that the request. So basically, what happens here is that the same server is going to end up receiving the WebSocket edit, and how the same server ends up receiving is a whole another lore, but it's going to end up receiving it. And essentially, what we're going to do is we're going to iterate over this map of the document itself. So let's say these two docs are called doc1, and we'll iterate over the map that this doc has. And what we're going to end up doing is that for the user who send it, we'll ignore obviously their entry within the map, but we'll send it to using Aryan's WebSocket object. We'll actually send back the edit to Aryan's client, and that's how Aryan actually ends up receiving it here. And the WebSocket library or package that would be end up getting used over here on the server when you're actually writing the server usually has a send method which would take in a WebSocket object. So we would put in Aryan's WebSocket object, and we would actually send sort of the edit that has been written, which eventually reaches Aryan's page. Now, this is generally how WebSockets work, right? Where you have the user interface, which creates a persistent WebSocket connection with the server. A WebSocket object is generated. We store it in a map in memory, in a hash map, in a document, not in a database, because a database cannot store these WebSocket objects. And secondly, um, whenever we get a new request, whenever the server receives a new edit, we iterate over this map and we send it to everybody else who needs to receive this edit, who is basically currently on the dock. Now, there is one problem here, and that is what I've touched upon here, which is why simple auto scaling does not work. Auto scaling here essentially refers to if there are 5 different people, right? If there are 5 different users, we can essentially have one server, and the initial WebSocket connection. So when this client or this user interface is trying to connect with a server, we just have one server, and in memory we'll have this one single hash map, right? However, let's say we're having 1,000 millions of users. Let's say we're getting not even Google Docs scale. Let's just say we have 2,000 users, right? A server that has less memory, less compute, less storage, less RAM, essentially, would not be able to store that many WebSocket objects in memory. And also, whenever so it wouldn't be able to store it in memory, which means that we need multiple servers. Now, if we need multiple servers, what we're also saying is that this user interface can, in theory, connect to any one of these servers. We actually don't know that the document one actually lives on the server one. We actually don't know that document 5 actually lives on server 3, like all the people whose WebSocket objects are stored. And what this entails is that whenever we create the initial WebSocket connection, it could go to any one of these servers. Why is that a problem? Because let's say Kunal sends out a request. Kunal is the one who sends out the initial request to connect to the document, and their document is connected to server 1. Aryan also gets connected to server 1. However, when Anish comes on the app onto the dock, there is no guarantee that Anish's WebSocket request connection is also going to server 1. It can go to any other server theoretically. If it's round robin or if it's consistent hashing, whatever it is, it could in theory go to S3, let's say. The problem with this specific architecture here is just simply the fact that whenever, how I initially talked about, these WebSocket objects are what are used to actually send back the bidirectional communication, right? So whenever, let's say, an edit is received, whenever this edit is received by server 1, because Kunal was the one who made the edit and his WebSocket connection lives on server 1, therefore through the WebSocket connection, that's where the edit would come in. We can only iterate over the hash map that exists on server 1, and we actually wouldn't be able to reach Anish's WebSocket object because it actually lives on server 3, which is a problem because these aren't stored in a central database somewhere else. These are stored in memory, and this can't be accessed on server 3, if that makes sense. So in that case, only Aryan will receive the edit. Anish would actually never receive the edit, which is a problem that we need to solve for. And how we can solve for that essentially is by introducing a key value store. What we can do in this key value store is the fact that the documents, essentially, what can happen with these documents is when Kunal creates that first connection to actually connect over a WebSocket connection to server one, we can in a key value store the document ID, so doc1, versus the server ID. What that means is that whenever, let's say, Aryan now comes in to actually see that, okay, I'm trying to create a WebSocket connection, when the request hits the API gateway, which is essentially the layer before we actually expose all of the servers, we actually check in the key value store, okay, do we have a document one that, because Kunal is, Aryan, sorry, is trying to connect to document one. So do we have a document one that exists within this key value store? And the key value store would say yes, because Kunal actually exists on server one with his WebSocket object. So the request gets routed to server one. And the same thing happens with Anish. This request from the UI comes to the API gateway. We see that Anish is trying to access doc1. We check in the key value store. Okay, cool. Doc1 is present on server 1. This goes here. So essentially, this part now, if I can copy properly, now all of doc1's WebSocket objects live on server 1 itself. And this is sort of one hacky way to be able to solve this problem. This is not always used in production grade systems, and in actual production systems, we actually use something else that is called the publisher subscriber model, or the pub sub model. And that is actually what is used for WebSocket scaling. And that is something that I will talk about potentially in a next video, sort of thing, but definitely not right now, because it's a whole different architecture that is used in a lot of real-time applications, whether it's chatting apps, Google Docs apps, or whatever else it is. And however, we've currently solved the problem within the scope of this dummy project that we're trying to create, essentially. And therefore, what we end up doing here is we end up having this KV store that stores the document ID with the server ID. This is not the most ideal, because now you also need to maintain a key value store, and we're now creating more surface area for things breaking. However, for the limited scope of what we're trying to achieve, this works fine and it will be fine. So that was the part about why simple auto scaling doesn't work and how WebSockets actually scale. And the next part is mostly understanding about how edits work concurrently. So obviously, so far we've talked about edits happening over WebSockets, right? All of this is a real-time connection. All of these edits are traveling over WebSockets, bi-directional communication. We're using the WebSocket objects of all the users. However, we can also have conflicts. And the conflicts I talked about earlier, which was that theoretically, multiple users could edit the same piece in the line in the document at the same time. And how that is resolved commonly within Google Docs is using something called OT, which stands for operational transforms. It in itself is a really complicated problem to solve. And CRDTs is one of the other ways. And CRDTs is actually used outside of Google Docs in a lot of different real-time use cases, whether it's game engines. So most of the common games we play would probably have some version of CRDTs, and other essentially real-time editing systems where you can edit or work on the same piece of the entity at the same time, and how that ends up getting resolved. And Google specifically uses operational transforms. And this isn't like a simple data structures algorithm. It's this is not a simple data structures algorithm sort of thing. This is an extremely complicated thing which has multiple resource papers on it. It's still being talked about, it's still researched about, and honestly, even I know very little about it. However, that's one of the things for how conflict resolution works in complicated systems like these. And mainly, lastly, I wanted to talk about optimizations. So one optimization is using CDNs. CDNs stand for Content Delivery Network, and what they're responsible for doing is serving static assets, which means that what they're responsible for is being able to serve static files much quicker. So it can be static files like these Google Docs. It can be, let's say, images or any other assets, really. And all of this is usually stored in a CDN. And that's a very common use case of a CDN. And a common example of a CDN is something like CloudFront. Even I think AWS has its own version of a CDN. I've never used it. I've played around with CloudFront. I think AWS has its own version. Not too sure, but yeah, those are examples of a CDN, and that's one of the optimizations to add, so that essentially what is in this browser can load essentially much quicker, because CDNs are present at several edge locations where you would get these files much quicker accessed. And the other optimization to think about is the publisher subscriber model for WebSocket scaling. So, earlier here I talked about the KV store being an essential sort of workaround to get around working with working with WebSockets over, let's say, 1,000 users on the application. However, the ideal architecture is using something like a publisher subscriber model. And if I were to summarize the architecture here in a singular diagram, so whenever the user interface actually requests for the document, ideally we get it from an optimized CDN, which can get us the document quicker. All the edits are happening over a WebSocket connection, which is initiated with these servers. And we have this key value store here, which defines which server does our WebSocket connection need to live on. And each of these servers, when they receive a new edit, publish to a queue, which eventually goes into a database. And we have workers, which on a cron, which every 30 minutes would extract all of these edits per document from the database, would compact all of them into a file, and eventually send it to S3. And eventually the cycle repeats. The couple of loopholes here that I already know are, firstly, the race conditions I talked about, where theoretically the worker could, because it's running only every 30 minutes, and AWS S3 is only going to get updated every 30 minutes. If between those 30 minutes we're requesting the doc again, it's going to be a problem. And the bad solution workaround is to compact all of the edits from the database along with the file that is coming from S3 and then serve it to the UI. But then the CDN becomes useless, so that needs to be tackled. And these are sort of the more complex race conditions to think about, that I would think about if I was actually building Google Docs, but I'm not. And yeah, I think these are some of the interesting high level concepts that I've thought about previously. If I were building a dummy Google Docs, and that is mostly it. And the next thing that I would really love to talk about is the entire pub sub model for WebSocket scaling, and how it's used in, WhatsApp and a bunch of other real-time applications. And that is something I'd really love to talk about, and that is probably what I would end up talking about. So that should be it for this one, and I will figure out what to talk about next, basically. And I know what I will. It's the pub sub model.